Hello again. This is Math 2245 for the summer of 25, and the name of this video is Linear Programming Lecture. Now this video is best viewed as an active learner with pencil and paper at hand and, as needed, ample use of the video controlled buttons. Play, pause, and rewind. There are many situations in business, politics, economics, military strategy, and other areas where one tries to optimize a certain benefit, and you might be maximizing a profit or minimizing a cost. And so what we're going to do is we're going to be talking about an optimization process, and we're going to focus only on linear programming. It depends on properties of convex sets and hyperplanes. And that's what this lecture is about. Now, since the 1950s, the variety and size of industrial linear programming problems have grown along with dramatic increase in computing power. Still, at their core, linear programming problems have a concise mathematical description, and we'll discuss that here. And so we'll discuss the geometric view, which provides insight for visualizing the algebraic approach that you need for larger problems. So, generally speaking, a linear programming problem involves a system of linear inequalities in the variables x1 through xn and a linear functional f from Rn into R. Now this means the range of the linear function is a real number. It's a scalar. The system typically has many free variables, and the problem is to find a solution x that maximizes or minimizes f of x, which is going to be called our objective function. Here's an example. The Shady Lane Grass Seed Company blends two types of seed mixture, evergreen and quick green. Each bag of evergreen contains 3 pounds of fescue seed, 1 pound of rye seed, and 1 pound of bluegrass seed. Each bag of quick green contains 2 pounds of fescue seeds, 2 pounds of rye seed, and 1 pound of bluegrass seed. The company has in inventory 1,200 pounds of fescue seed, 800 pounds of rye seed, and 450 pounds of bluegrass seed available to put in its mixtures. The company makes a profit of $2 on each bag of evergreen and $3 on each bag of quick green that it produces. Here we're going to set up the mathematical problem that determines the number of bags of each mixture that Shady Lane should make in order to maximize its profit. So first we will let x1 and x2 represent the number of bags of evergreen and quick green respectively. The problem can be summarized mathematically as this. We want to maximize what we're going to call our objective function, that is 2x1 plus 3x2, that's the profit function, subject to what we will call the constraints. These are 3x1 plus 2x2 is less than or equal to 1200, that is the fescue constraint. x1 plus 2x2 less than or equal to 800, that's the rye constraint. And x1 plus x2 less than or equal to 450. That is the bluegrass constraint. And we also have non-negativity constraints. x1 must be bigger than or equal to 0, and x2 also must be bigger than or equal to 0. Here's a second example of a formulation. An oil refining company has 2 refineries that produce 3 grades of unleaded gasoline. Each day, refinery A produces 12,000 gallons of regular, 4,000 gallons of premium, and 1,000 gallons of super at a cost of $3,500. Now, each day, refinery B produces 4,000 gallons of regular, 4,000 gallons of premium, and 5,000 gallons of super at a cost of $3,000. An order is received for 4,800 gallons of regular, 3,200 gallons of premium, and 20,000 gallons of super. Set up a mathematical problem that determines the number of days each refinery should operate in order to fill the order at the least cost. This, of course, is a minimization problem. So here, we're going to let X1 and X2 represent the number of days of operations for the respective refineries. The problem can be summarized mathematically as this. We want to minimize the objective function, which in this case is a cost function, and this is 3,500 X1 plus 3,000 X2, subject to the constraints. This is 12,000 X1 plus 4,000 X2 bigger than or equal to 45,000. That's the regular constraint. 4,000 X1 plus 4,000 X2 bigger than or equal to 32,000. That's the premium constraint. And 1,000 X1 plus 5,000 X2 bigger than or equal to 20,000, and we're letting X1 and X2 be bigger than or equal to 0. Notice that you could do some scaling if you were working to solve this and find the solution through a process that would fit better graphically. So here is the definition of the general linear programming problem. So given a V equal to a column V1 through Vm in Rm, C is equal to C1 through Cm in Rn, and an M by N matrix A being Aij, then the canonical linear programming problem is as follows. Find an n multiple x equal to x1 through xm in Rn to maximize an objective function, which is f of x1 through xn, and this is equal to c1. Again, it's a linear c1 times x1, c2 times x2 plus all the way up to cn times xn, subject to some constraints. And you can see these constraints are given as linear constraints, and this is less than or equal to b, and xi is bigger than or equal to 0. Now, when you look at these linear constraints, you realize that looks like a matrix, and so we can even have a matrix formulation of this as well. And here's the vector matrix notation. And so we want to maximize f of x is equal to, this is C transpose times x. Now some authors write this, and this is a dot product, but this is exploiting the fact that a vector is also a matrix, so we could talk about the transpose of that. So we're saying that this can be listed as maximize f of x equals C transpose x, subject to this constraint ax is less than or equal to b and x bigger or equal to 0. Where an inequality between two vectors applies to each of their coordinates. Now, any vector x that satisfies what we show here as 2 and 3 is called a feasible solution. It could be used in the problem. And the set of all feasible solutions, denoted by script f, is called the feasible set. Now, a vector x bar in f is an optimal solution if f of x bar is the maximum over all x in the feasible set of f of x. Now, this really is not so restrictive, because you see you could talk about changing the problem with the constraints. For example, to minimize a function h of x, you replace the problem with maximizing the function negative f of x. And if you have a constraint of the sort where this linear equation is bigger than or equal to bi, you just multiply both sides by a negative and you get this similar constraint. And if you have an equality constraint, what you can do is say, well, the equality constraint is listed by 2 inequality constraints. You can have being less than or equal to b sub I, or the negative being also less than or equal to b sub I. Then it's bigger than and less than. That means it is in fact equal to. Now, with an arbitrary canonical linear programming problem, two things can go wrong. The feasible set could be empty if the constraint inequalities are inconsistent, or the objective function takes on arbitrarily large values in the feasible set. And that means that the desired maximum does not exist as a finite number. It blows up. Now, in the former case, we say the problem is infeasible, and in the latter case, it's called unbounded. Fortunately, these are the only two things that can go wrong. And so we have the following theorem. If the feasible set is non-empty and the objective function is bounded above on the feasible set, then there is at least one optimal solution. Furthermore, at least one of the optimal solutions is an extreme point of the feasible set. Now, you should realize that the feasible set is a solution to a system of linear inequalities. Geometrically, this is the intersection of a finite number of closed half spaces, and sometimes in dimension you'll call this a polyhedral set. And so intuitively, the extreme points correspond to the corner points or vertices of this polyhedral set. And we may talk a little bit more about that later in this course, or not. We'll see. So let's finally solve a problem geometrically. So here, example says, maximize this objective function, f of x1, x2 is equal to 2x1 plus 3x2, subject to constraints. x1 has to be less than or equal to 30, x2 less than or equal to 20, and x1 plus 2x2 less than or equal to 54, and x1 and x2 must both be non-negative. Well, we graph the constraints, and so we're graphing the constraints, and we find that there are a bunch of corner points, and you see that this is the slope of the objective function, which is also linear, and so here you see that it is equal to 30. On this line, it's equal to 60, but on a corner point where it has to intersect the set because it is convex, one of your maximums is going to be achieved there. Now, operationally, this is sort of a proof of the theorem for a two-dimensional case. But down here, you can see that what you will do is you'll find the intersection points of these things, and you will look at the feasible region that's shaded here, and you will just have to evaluate the corner points. And so here I am evaluating the feasible, this is 2x1 plus 3x2 at all the corner points, and I find that the optimum is 96, and that's achieved when x1 is 30 and x2 is 12. Now here's a three-dimensional problem, and the geometry is a little harder. Here we're to maximize f of x1, x2, x3 is equal to 2x1 plus 3x2 plus 4x3, subject to these two linear constraints and these three non-negativity constraints. Now, the quadrilateral surface BCDE, which is this top part, forms a boundary of the feasible set on the top. And the non-negativity tells you that you're bigger than, you're in the first, I'm going to call it the first octant, because all three of those variables are non-negative. But beyond that, the two planes that we have, and here's a drawing of the other plane, form another bounding surface of the feasible set. And so you see the vertices of the feasible set are shown here. We have A, B, C, D, E, and the origin 0, 0. So this shaded thing is the feasible set in 3 dimensions. Now, when you look at the corner points, though, you see that you have x1, x2, x3 values. We plug it into the objective function, and we pick the biggest one, and that is going to be b, and that is going to be 130. Now, I am giving you an LSA to do, and it's going to have multiple parts, but I'm going to ask you to solve this problem graphically. And so I'm asking you to graph it. You'll find the extreme points by solving systems of equations, and then you'll plug these into Excel and find out what is the optimal solution. There's more to this LSA that come later in this video. But what about really big problems? Well, it turns out George Dantzig, I'll talk more about him in class, invented the simplex algorithm. And many textbooks will have you do the simplex algorithm by hand, and it is instructive to think about that. But I will not ask you to do this during summer 25 at COD. I will cover briefly elements of the algorithm, however, and then I will ask you to formulate larger LP models and use technology, Excel Solver, to solve them. More later about this LSA. So this is his simplex algorithm. So, and these are the steps. Now, I'm just really instructing you. You're not going to have to do this, but I am going to make a few comments about this. Change the inequality constraints into equalities by adding slack variables. This is an important step that was pretty clever, actually. And we're going to let m be a variable equal to the objective function value, and below the constraint equation, write an equation that is the negative of the objective value plus m is equal to 0. Then you set up what is called an initial simplex tableau. And here, again, this is more cleverness, the slack variables and m provide the initial basic feasible solution. So you see you're starting with the slack variables. And then you have a check for optimality. You check the bottom row of the tableau for optimality. If all the entries to the left of the vertical line are negative, then the solution is optimal. If some are negative, then you pick, this is an algorithm, the variable xk for which every entry is as negative as possible. And so you're picking the most negative value. And you're going to bring the variable then xk into the solution. Now you do this by pivoting. You see these words should sound familiar. On the positive entry a pk, for which the non-negative ratio bi over a ik is the smallest. This new Basel solution includes an increased value for m. You see, my dear students, his simplex algorithm, you always move to a better solution. And you repeat this process because it's an algorithm until all entries in the bottom row are non-negative. That means you found the optimal solution. I'm not going to make you do that, but I thought it was useful for you to understand what that was about. And so here is a problem that we're going to solve. This is 3-dimensional, and you want to take the time to write this down, but you see we're maximizing a 3-dimensional problem subject to those linear constraints and these non-negativity constraints. You may want to write this down to follow the discussion. Now we're going to solve this using Solver. And this is a little bit of tradecraft, but a lot of times when I'm lecturing on something, I will copy the problem and paste it here just so I know what it is. Now I do it this way, you can do it other ways. I create in Excel a place, and I'm highlighting this where my variables will go. And you see this is going to be x1, x2, x3 in this order, x1, x2, x3. So that's where I'm going to put my variables. I also, in Excel, usually create a spot which is going to be my objective function. And so that is going to be this part here, and I make it yellow just because I'm going to see it. And then I create a space where I'm going to put my constraints. Now the constraints will have a left-hand side. They will have a bigger than or equal to, or less than or equal to, or at least they will have signs, S-I-G-N-S, in the middle, and these are the constraints right-hand side. So for example, the constraints are going to be here. I'm going to have 3 of them. I will put x1 plus 2x2 in here. I'll put 2x1 plus 4x1 in there. And I'll put x2 plus x3 there. These are all less than or equal to, so I'll make sure I'll make note of that. And then I will put 28, 16, and 12 over here. Now, I'm using Solver to do this, but this is what I set up in Excel. Now, to access Solver, you will, in Excel, go to this Data tab. Now, depending on your version of Excel, and you can download this, and Jesse Hayes Carver can help you do this if you need to, but you can download the data option. It may be there as a standard thing. I really don't know about the Excel you're going to be looking at, but I am looking in Data, and I have Solver activated over here. So that's what I'm going to be clicking on, the Solver, and that's how I'm going to proceed from here with the function and solving the problem using Solver. One thing that will happen as you see this, you will see Solver ends up putting some dollar signs there. These are called absolute addressing as opposed to relative addressing. I'm just really putting this in here in case you need to understand this from Excel. You might want to pause this or look this up yourself and read about it. You don't need to do this, but you'll notice that Excel does do this, and so it will do absolute addressing for you, and that's kind of a very nice thing for your solution. Okay, so let's see what we're going to do. The first thing is I'm going to set the objective, and so I go up and I click. I clicked on Solver, and here's what Solver looks like. So it says set the objective, and so I'm going up here into this. Looks like it is K2, and I'm clicking on that. Now Excel says that that's going to be absolute addressing K2 because that's where the value of the objective function is going to be seen. And we're going to want to maximize the objective function in this problem. So I click here. You see you could do different things with this. And we're going to maximize this objective function by changing the variables that are here. And I just go up to, this is going to be H3 to H5. Again, that's absolute addressing. That's where the values of your variable are going to be. And we're going to also add a constraint. This is a checkbox, but I'm going to make my unconstrained variables to be non-negative. I still have to show you how to do the constraints, but I will show you that. Okay, so that's what we do first. And so we'll go to the next thing in the screen. Okay, and so this is what I end up typing into those fields. And so you see, and my variables are over here at H3, H4, and H5. And so I'm going to say that the objective function is equal to, because it's an equation in Excel, and I type in the objective function. And then I'm going to type in the constraints. Now these are the left-hand sides of the constraints, and I'm clicking up here to get the values of X. So I type those in. And I also type in the right-hand side constraints over here. The right-hand side values for the constraints. And so this is what I'm doing so far. And I showed you that this non-negativity was a checkbox in Solver. You do have to do that as well. This is how I add the constraints. And so what I will do is there'll be cell references. And so what I will do is I will go over here, and this is subject to the constraints. I will go up here, I will click and pull down. And notice, my dear students, that what happens is that we are adding, oh, well, first of all, this is the left-hand side. So I pull down here, that goes in here. This is less than or equal to. You notice this is a pull down menu. I could fix it to be differently if I want. And here's the constraints. That's where I pull down the right-hand constraints. So I'm using this, and then I add the constraint. And once I add the constraint, I have this problem here. So I've set the objective function. I said it was a maximization. I told it where the variables were going to be. I told them what the constraints were, and this is how the constraints are listed. I made the variables unconstrained, and I selected that we're going to use the simplex linear programming method. Now, Solver is actually a very powerful tool. You could do many other things, but we're doing this right now. And so with that, I press the Solve button. And Solver works. And so it says the optimal value of the objective function is 70. The variables are x1 is 6, x2 is 11, and x3 is 1. And notice that I used up all my constraints. Sometimes there is not all the constraints are used, but that's what I get. That's how Solver works. Now, I am going to give you some additional LP problems in the same LSA. Two of them are going to be modeling problems where you have to read and model, and the third one is going to solve a four-dimensional problem in Solver. And so those are going to be contained in the announcement, and eventually I'll put up an upload space for those. In closing, please take care. I look forward to seeing you in class.